Good, thanks. Thank you. Okay. I hope you had a great lunch. So let's go. So this morning, we had Emmanuel showing us all the different representation with which we can represent some small molecules. And I will talk about the one on the far right, the one in which we have the coordinates of each atom. And for these models that works on coordinates of atoms, there's one property that is really important to have, is to be equivariant. So let me explain what this is. So if you have a molecule and each atom has coordinates, it's arbitrary the way you choose your axis to represent the coordinate of each atom. So on the left, I have one choice of axis, and on the right, I have another one. And as you can see, the numbers are completely different, though they are just related by a rotation. But if you don't do anything and you just take a fully connected neural network to train your model to learn energies or chemical properties, your network will have to learn that these two representations are the representation of the same object. And the aim of imposing equivariance in your model is to do this job for your model, to make your model know this from the start before even it has to start learning. And yeah, there's another way to fix that. It's just that augmentation. It's easy, but it's inexact, and it takes a lot of data and takes time. But if you use equivariance, it's exact, and it's actually more data efficient. I'll show you later what I mean by that. But before, I want to give a more deeper explanation of why equivariance is so cool. And it comes from physics. And so all the models we have to explain our world that work well, like mechanics, fluid dynamics, electrodynamics, standard models, they are all equivariant to different group of symmetries. So I've listed a few on the left that are the most relevant: rotation, translation. It's a bit annoying that there's a... And time, translation, and boosts that you cannot see. Thank you. And all these models are equivalent to these symmetries, and actually much more, especially for the standard model. I heard that there's like a lot of symmetries, weird symmetries. So physicists end up realizing that the world is actually following some symmetries, and that's actually very much deeply grounded into the description of reality. And that's actually the starting point of many theories, especially in like field theories, quantum field theories. So yeah, all these models are equivalent to these symmetries, which means that all the things they predict are equivariant functions. And why not having our neural network that are also following the same rules? Just to give some example of task for which equivariance is useful. Let's say you have a molecule and you want to take as input the position of each atom, and you want to predict the forces. This is equivariant because if you rotate your molecule, it rotates the force with it. Another example, that's predicting the Hamiltonian. On the left, you have the input, which is the position of your molecule. In this case, it's just a water molecule. And on the right, you have an Hamiltonian. It has actually a block structure. It's hard to see. And what's going on here? You can see the values on this Hamiltonian changing in time while we are rotating the molecule. These are actually just due to the rotation. And so if you don't need to learn that, and this is just known by the network from the start, you gain a lot of time training your model. These are a non-exhaustive list of models in the literature in machine learning that use equivariance. It's a lot used, like for instance, in protein folding, protein docking, molecular dynamics. This image is the example I know the biggest thing that has been simulated is using an equivariant neural network. It has like 44 million atoms and was running on 5,000 GPUs. And it was using an equivariant neural network. So yeah, okay. And I was saying using equivariance in neural network is good for data efficiency. And this is an observation I like a lot, but I have no explanation for it. And I hope there will be more observation of this and maybe an explanation one day. If you take a neural network and you retrain it for different size of training sets. So you have a big training set and you make smaller training sets with it. You just take a subset of it. And for each of these subsets of your training set that are bigger and bigger, you retrain your neural network from scratch, and you check what you do as a generalization error. And if you do a plot in logarithm, very often, and we don't really know why, that's what I think Emmanuel or Daniel was saying this morning, we observe a power law behavior. And when you use equivariant feature in your neural network, and I'll explain later what I mean by invariant and equivariant features, this power law gets steeper. And this is a very cool observation because it shows that it's more than just data augmentation. It means that if you double the size of your training set, it will divide by a larger number your error than just doing data augmentation. But because, yeah, the naive intuition behind data augmentation would be that you divide your error by a number, but here it's like the power law is different. Anyway, so now let's do some math. So I want to explain what is equivariance in a mathematical way, and for that I need to explain what is a group and what is a representation. I can explain what is equivariance and give examples on how to create a neural network. What's the basic tools, mathematical tools we need to create an equivalent neural network. So let's start with group and representation. So a group describes a set of operations and how they compose. How they compose means if you pick an operation in your set of operations and another one, and you apply the first one and the second one, what do you get? You get actually the same as if you had picked that composition in your set of operations. It doesn't tell you anything else than that. While a representation tells you how a vector space behave when you act on it with an operation in your group. If I give examples, a group can be the set of rotations. All the rotation is a group. In parity, like inverting space is also a group. But if I give an example of representations, you have scalars, which are quantities that are unaffected by your operation in your group. Or you have vectors, like for rotation, vectors are like things made out of 3 numbers and rotate. I guess you know what I'm talking about. Pseudo vectors and so on. So mathematically, to define a group, you just need a set that follows 3 rules. You need, in your set of operation, you need an identity operation, which means that if you compose this operation with any other operation in your group, it does not you don't get anywhere else. The composition with the identity leaves you where you are. You need associativity, which intuitively it's a bit hard to explain, but that's actually crucial. And you need an inverse for each element of your group. So that's actually very important. If you take two elements in your group and you compose them, there must exist another element in your group that allows you to go back and revert that operations. Now, what's a representation? You need two things to define a representation: a group and a vector space. So this small g is an element of your group. The small x is an element of your vector space. And again, you have a set of rules you need to follow to be a representation. The first is that it's a linear operation. If G acts on X plus Y, it must be that it's equal to acting on X, then acting on Y, and summing the results. Let's say you have two vectors. If you rotate both and you sum the results, you get the same thing as if you sum the two vectors first and then you rotate the results. And last, it needs to follow the same structure as the group, which means that if you have two elements on your group that you first compose to get another element in your group, and you apply that to X, you get the same result as if you apply each of the element of your group one after the other to X. And there's an equivalent notation using matrices that I will use later instead of this d of g comma x. So because it's linear, representation is linear, if your vector space is of finite dimension, you can represent this linear operation as a matrix. In this case, you will write it as dg as a matrix, apply on x by matrix vector multiplication. In this case, following the structure of the group is now expressed this way. The matrix that represents GH is equal to the product of the two matrices that represent G and the matrix that represents H. So let me go through an example. Let's say you have a vector of dimension 9. So you have 9 numbers, and we want to say how they behave with respect to rotation. So from now on, I will only talk about rotations. That's the group that is the most relevant in this field. The representation, they act like a data type, but to tell how the numbers are affected by the rotation. Let's say the 3 first are scalars. What it means that these 3 numbers, whatever you apply as a rotation to your molecular input of your model, they will never change just because of this rotation. They can change because of other things, but not rotation. Let's say the 3 following numbers, they get together and they form a vector. And let's say the same for the last 3. And what it means is that now when you rotate your system, or there's 2 ways, either you rotate your system or you change the coordinate, you apply a rotation to your axis with which you measure things. That's equivalent actually. If you do that, you can relate this vector that you had at first. You can relate it with the new vectors by a matrix that contains this rotation. And this matrix will be block diagonal and have a lot of zeros, because to know how let's say this vector gets mapped to his new value, you don't need to know what's the value of the other vector. They transform independently with the rotation. And now we have the tool to say define mathematically what is equivariance. So to define what is equivariance, you need two vector space. Let's call them V and V prime. And you need representation that acts on this vector space, which means you need to know how rotation affects vectors in these two vector space. Let's call them D and D prime. They can be different. Equivariance is a property of a function that goes from one vector space to the other. And it's the following property. If you first take a vector in your vector space V and you apply a transformation D of G to this vector, so you rotate your system and this vector gets sent to another vector in the same vector space, and then you apply your function f. This is how you would write it mathematically. F is equal to D of G of X. If this is, if now you do the reverse, you take the same vector X, but you first apply F, so you end up in V prime. And now you apply the rotation in V prime. So you need to now use D prime to rotate your vector that is in V prime. So you would write that D prime of G applied to F of X. If these two are always equal for all G and for all X, then your function F is equivariant. So now if we go back to that initial like physics motivation with the different models in physics that are all equivariant, these models actually can be fully defined through a single function that's called the Lagrangian. That's actually crazy cool. The Lagrangian is just a scalar function of the state of the physical state that you want to describe. And these Lagrangians are invariant to all these symmetries. So which means that it's a special type of equivariance, it's invariance. It means that if you apply D of G to your physical state, and then you compute the Lagrangian of that new state, you get the same value as if you just compute the Lagrangian of your state. And from this Lagrangian, we can derive all the physical quantities by taking derivatives of this Lagrangian. And taking derivatives of the Lagrangian gives you equivariant functions. And because of that, everything you want to predict using one of these physical model will be an equivariant function. So if everything that physics can describe is our equivariant function, we should do the same with machine learning. So now let me explain the basic tools we need to create an equivariant neural network. So I've listed them here. Basically, the first one is composition. If we can compose functions that are equivariant, we make an equivariant function. So that's very useful because you can create your equivariant model by looking at each element, if each of its constituents, and make it equivariant, and then the whole thing is equivalent for free. And then, yeah, maybe let me just go through each slide. So composition, as I said, you have two functions, let's say f and h, that are equivariant. If you can prove that the composition is equivariant, because if you rotate your input x with the first representation that acts on V1, and f is equivalent, you can swap that D1 for this D2 that acts at the output of f. And then because h is also equivalent, you can trade this D2 for this D3 outside of h. And now if you read the very first left-hand side with the right-hand side, it means that the composition HF is equivalent. And now if we have like basic arithmetics that we can make basic equivariant operations. We can do everything. Because with basic arithmetic, we can make basic functions, and then we can compose basic functions, and we can make literally any function we want that are equivariant. The first thing to observe is that if you have two functions that are equivariant, if you sum them, it's still equivariant. That's also very simple to see, and that comes by the linearity of the representations. And if you multiply a function by a scalar, an equivalent function by a scalar, it's also it gives you also an equivalent function. Okay, now comes the most interesting and the most difficult mathematical tool we need, basic tool we need. It's called the tensor product. It tells you how to multiply two quantities that are equivariant to create another quantity that is still equivariant. And in its simplest form, the tensor product looks like that. If you have two vectors, you can create a big matrix by basically computing all the pairs of multiplication you can do. x1 times y1, x1 times y2, x1 times y3, and so on. If you make that, it's actually equivariant. You can show that this big matrix, I mean, it will, if you rotate the two inputs x1 and y1, it will change completely the resultant matrix. But it happens that the way it changes fulfills the requirement to be a representations. So that's good. The downside of this operation is that, as you can see, it increases a lot the dimensionality of your vector. So if this is a vector you use to featureize your layer in your neural network, and you have another quantity, if you just use tensor products like that, you increase the size of your features indefinitely. So that's a downside. But there is a solution. The representation you get when you make a tensor product is actually a so-called reducible representation. What does that mean? A representation is reducible if there exists a subvector space, let's say W in V, such that if you restrict your representation to this subvector space, it is still a representation. And that's probably obscure. So let's look at an example. Let's take the example of the tensor product of two vectors. Like, I mean, I'm still talking about rotation. So two vectors, you know how they behave with respect to rotation. This 3x3 matrix contains actually subvector spaces that are that transform independently. The first of them, you will recognize it, is the trace. So if you sum the element in the diagonal, you get x1 times x2, y1 times y2, z1 times z2. And this is nothing else than the dot product. So, and the dot product is a representation by itself. So if I take two vectors and I do the dot product, the result I get is unaffected by a rotation of the two initial vectors. If I rotate the two initial vectors and then I do the dot product, I get the same result. So this is a subvector space of our 3x3 matrix. Another one is the anti-symmetric part. So if I take these two components and I subtract them and do the same for the others, what I get, you can recognize, this is the cross product. And this is also the same story. This is also, it also transforms independently with respect to rotation. if you have two vectors and you do a cross product, the result is rotated the same way as you rotate the two inputs. These two things rotate together. And you don't need to know the value of the dot product to compute to know how the cross product will rotate if you rotate the inputs. And so here we have 1 plus 3 degrees of freedom in our matrix. It happens that the remaining degrees of freedom, which is 5 of them, also transform independently with respect to rotation. So we found all the degrees of freedom. 3 times 3 equal 1 plus 3 plus 5. The one is the dot product, cross product, and that's the symmetric traceless part. It's the remaining, which is also a representation of rotations. So, and these representation we found, in the scalar we knew it, the vector we knew it, this new one we just discovered it. They are all so-called irreducible because we can't split them further in smaller pieces. So these irreducible representation, they are the smallest building blocks of representation of your group. And they are known. For each group, you can think about, you can find some math book that will tell you what are the irreducible representation of that group. Let me tell you which are the irreducible representation of rotations. They are indexed by integers, 0, 1, 2, 3, and 4, and so on. There is an infinite number of irreducible representation of rotations. For each of these integer L, they are of dimension 2L plus 1. So I've put a small list here. This list is infinite. I've put on the right the name they have. So the first one is called scalar. Second one I call vector. And then they don't have any names, but there's infinitely many of them. Now, if we look at rotation plus what I call parity, which is an inversion of space, it's a little bit of a bigger group. It doubles the number of irreducible representation. Now you still have this L to index them, but you have another index to represent how they behave with respect to parity. The parity is either even or odd. And again, I've put the names. So if you are even with respect to parity and you are L equals 0, you are scalar. We call it a scalar. If you are odd with respect to inversion and dimension 3, it's a vector. Otherwise, it's pseudo-scalar, pseudo-vector. Yep. And so the rule that, remember that thing 3 times 3 equal 1 plus 3 plus 5. This was the rule how to decompose the tensor product of two vectors into irreducible components. Mathematician a long time ago found the general rule for any two irreducible representation. You take L1 and L2 that are two irreducible representation of rotations. And how do they, and you make the tensor product, you might wonder how this tensor product can be decomposed into smaller irreducible pieces. And this is the theorem. It's called the Clebsch-Gordon theorem. And the solution is that you simply have to do L1 minus L2, take the absolute value, and that gives you the L of the smallest dimensional representation you can find in this tensor product. And they all appear until L1 plus L2. If we look at this and we take the example I've shown here, Here we had two vectors. It was therefore L equal 1 for the two input for the two vectors. So 1 minus 1 gives you 0, 1 plus 1 gives you 2. So you get all the representation between 0, 1, and 2, which are of dimension 1, 3, and 5, because here it's the dimensions. And so this tensor product is actually followed by this decomposition into this irreducible sub-component. Is actually the most generic way to multiply two equivariant quantities together. So now we know how to sum them together. We know how to multiply them together and how to compose them. So with these three tools, we can already create all the polynomials that are equivalent. And with polynomials, we can already do quite a good job. Linear mixing. So this is very useful to make a neural network. Let's say you have a certain number of representation, and you want a linear map that gives you other representation, and you want this linear map to be equivalent. It happens that the only way to do that is by mixing the representation of the same kind together. So you can create this new vector, the first one, by linearly combine this vector and this vector, but it cannot depend on these scalars. Otherwise, it would not be either not be linear or not be equivalent. And so this is how you can typically make a layer that is learnable in your neural network by linearly mix your vectors and scalars among themselves, and then you use the tensor product to make the representation teach to each other, talk to each other. So yeah, these are the basic tools. With that, you can then take your favorite architecture like graph message passing, transformer, 3D convolution, and you can replace all the multiplication by tensor products, replace the linear layer by the one that only makes the representation of the same kind together, and that makes your neural network equivalent. And yeah, that's all. But just on this last slide, I have this again, this plot I was showing with the data efficiency. So actually in this plot, these two models were both equivariant, but one was only using invariant features, so features that are scalars and are not affected by rotation. If you make a kind of more expressive equivalent representation with features that do change under rotation, like vectors or L equal 2, then you are more data efficient. But I'm good. I'm done. So if you have, maybe we can go over questions.
Okay, hi. So it's not really only on what you said today, but I wanted to ask a comment on the fact that I read this very nice paper, which is Hitchhiker's Guide to stuff. I don't know.
Yeah.
And they also introduced the chapter of unconstrained GNNs.
Mm-hmm.
And I wanted to ask a comment on the fact that today we talked a lot about how overfitting is a problem and how we should put more physical bias into it, into the architecture, into whatever. And in the slide, unconstrained GNNs seems to favor putting a better optimization landscape, and so trust more the data-driven approach rather than keeping the harder a physical bias into the architecture. So although the authors are clearly sympathizing for this kind of architecture, because some of the authors of this paper also did some of the unconstrained GNNs, I wanted to have an opinion by you, by how you think that what we said today on keeping the bias relates to this unconstrained GNNs versus equivariant GNNs, let's say, if you...
So actually, honestly, it's an open question. I don't have the answer. Obviously, I have a personal preference, and my personal preference is baked into these, what I was showing here with the physics intuition behind it. But it is very true that in machine learning, it's actually very non-trivial how the dynamics is affected by your change in architecture. You can change very naive things, very simple things in your architecture, and then the learning dynamics is completely affected. And so sometimes you better do the most dumb thing and you have better performance results because the dynamics of your neural network is better. And unfortunately, that happens. So yeah, I don't know the answer, but we happen that we managed to train those equivalent neural networks for quite a few applications already. So it looks like it's working, but yeah, it's totally an open question. Yeah.
So thank you very much. I would like maybe to go a little bit back to the examples of representations. So maybe what I would like to ask, which is a little bit more basic, is I do not understand what do you mean with these three scalars, 3x06. This is the first part. And the second one is, I am also not understanding that well, what do you do with these vectors that I see that you have to put this rotation matrix. I see that in your example, but it's not really clear to me what magic do you actually do to flip it around? You know what I mean? Could you explain that further, like this one and the 3x0e notation that you have over there?
3x0e.
In the previous slides.
Oh, yeah. So these notations, they use these L. So 3x0e means that you have 3 times 0, L equals 0 representation. And the E is for the representation with respect to inversion of space, so which means even, they are unaffected by an inversion of space. And 1 O means L equal 1 and O means odd. So these are vectors that are affected by inversion of space. So I'm not sure what you asked for. So can you elaborate on your question?
Yes. So basically it was like, I see that you have to rotate these vectors. The ones that are a vector, you have to rotate it with a rotation matrix. That I understand. But what I don't understand is why you have to put it like that. So this is the way that you would need to rotate the whole system. Right?
Yeah, exactly. I see the question. I understand that. Yeah, you're totally right. You can just say, okay, you take this vector, you apply a rotation matrix to it, you get this vector, and that's done. But I wanted to show that the whole vector can also be seen as a bigger representation, but a bigger representation that has a lot of 0 in its matrix representation. So this bigger matrix contains a lot of 0 there, and it has subblocks that are just those rotation matrices you know about. And this big matrix transforms the whole vector in one operation to rotate it. Yeah.
Hi. When AlphaFold 2 was released, many people claimed it was doing so well because of the equivariance in the structure model. Now AlphaFold 3 is released and it doesn't actually use equivariance anymore. What are your thoughts on that?
I don't know. I mean, I guess it's very much related to the first question. That when you don't enforce equivariance, it's easier to train. Actually, when you want to enforce equivariance, and you write your code in PyTorch or JAX, you will need to write like much more instruction to do the one layer. And because you have so many calls to your primitive operation in PyTorch, it slows down the whole operation, and it gets very memory consuming. So when you gain equivalence, you also lose a lot in performance. And because of that, you train slower, and there's a trade-off. And I guess they went for the simplest, the more like the faster training. I have a big hope that we can do even better than AlphaFold 3 using equivalence. I'm quite convinced. But for that, we need to accelerate the equivalent operation yeah.
Just a quick comment. Mass Jitterbug will be at Momol next Wednesday to present AlphaFold 3, so there might be a lot more conversation and answer about that.
Hi, thank you for the intro. This might be a really dumb question, but can you go back to the previous slide? Yeah, so this is a representation, right? And the two rotations in the block matrix, are they just going to be fixed according to the point group or whatever that the two vectors will be? And if that's the case, how do you represent this within like the neural network? Is that just going to be a fixed layer or something? Or
that's a very nice question. Actually, when you implement an equivalent neural network, you don't need to implement these rotation matrix never. That's actually quite a fun remark. You need those rotation matrices if you want to verify that your model is equivalent, because you need those matrices to rotate your input, then feed that to your neural network, and check that the output is the same as if you first just feed the network and then rotate the output. So you need those matrices, you need to code those matrices down if you want to check that your model is equivalent, but you never need them to implement your neural network, because what you need is these you need these rules to know how to decompose your tensor product into equivalent operations. And to do that, you don't need actually never to rotate anything. Did I answer your question?
Is that good?
I don't hear.
so in the end, I guess you'll be using the slide you just showed. Where
Which this one?
No, after you decomposed it.
You mean this one?
Yeah, this slide. Once you've decomposed it, you would only really be using those three features on the right that you've created.
On the
That are
right.
reducible representations. Is that what you're saying?
Wait, I didn't get it. I didn't get the question. So
When you're actually implementing the equivariant neural network, are you saying that you only actually use the stuff on the right after you decompose the tensor product? Yeah.
yes.
Okay, and then this would go into a regular neural network and they would check that it's equivariant at the end?
Yeah. If you want to check then these operations are equivalent, you will need to rotate the inputs and outputs. But this operation itself does not contain any rotation matrix. Yeah.
So this is the actual data that you feed into your neural network. Is that my question, I guess?
Yeah. Yes.
Work. Is that the case?
So say it again.
We can consider the S's as kind of your input and the Y as kind of the weight, learnable weight of your neural network. In this particular example, I think he's asking what are the learnable weight in this operation.
This operation has no learnable weights.
But if we were to implement the irreducible operation in a network, what would be the shape of that?
If you,
Am I?
so,
I think you can get.
yeah, we can discuss after.
Cool. Perfect. Let's thank the speaker once again, and then we can start the lab.